The Laplace transform is an elegant tool for converting differential equations into algebraic equations or other and hopefully simpler differential equations. So the way it works is like this. We take it for the general setup, some function on the half line. So this is for initial value problems, typically. And we take this to be piecewise continuous, which is actually more than you need. You just need the function to be integrable so that the integral of it is defined, and that's more general. But it's a good enough condition. And we want it to be of exponential order, which means it doesn't grow faster than an exponential. So in other words, there's some constants m and a for which this inequality will hold. And so this condition here, we say u is of exponential order. So this includes functions like constants, polynomials, exponentials themselves, trigonometric functions. It does not include things like e to the x squared. That grows too fast. It does not include the factorial, but just about anything else you can think of it includes. So with these conditions, so specifically piecewise continuous and exponential order, then the Laplace transform is defined. So we define the Laplace transform, and it maps the function u of t and transforms it into some other function which we'll call capital U of s. And the definition of u of s is that you find it by integrating from 0 to infinity e to the minus st against u of t. Okay. So once the t's are all integrated away, all that remains is a function of s. So then this transformation L is linear in virtue of its definition in terms of an integral. So if I replaced u with, say, f plus g, then you see that splits into two integrals, and then boom, you get to the sum of the Laplace transforms. And similarly, you can pull a constant out. It's also injective, or one-to-one. And so this means that different functions don't have the same Laplace transform. And this allows us to invert the Laplace transform, at least on its range. So if you know that the Laplace transform of f is equal to g, then if you're working around with Laplace transforms and you come with g, you can invert the Laplace transform just by replacing it with f. And so this amounts to basically using a lookup table. So I'm sure this is what you did in your previous differential equations courses. You go back and forth using the table. And sort of the magic property that makes it so useful is that if you apply the Laplace transform to the derivative of a function, you get, by integration by parts, s times us minus the initial condition u of o. That is easy enough to show with integration by parts. And so people refer to this by saying that the Laplace transform takes x derivatives and converts them into multiplication by s. All right, so this has the effect of transforming ODEs in t, maybe I'll say, into algebraic equations in S. At least, well, and we also have PDEs. Well, if it gets rid of the t part and turns that into just an algebraic equation, then the result will be an ODE. Oh, and I just realized that earlier I wrote derivative d dx, but that should have been ddt. So I'm going to make that little correction. Okay, and so these ideas here, these always work for constant coefficient. Equations, but just like L takes ddt to s, it also takes factors of t and replaces them with dds. Actually, it comes with a minus sign just to be difficult. But that means that if you have a non-constant coefficient equation, so if there are functions of t as your coefficients, then you can expect that maybe you'll end up with derivatives on the Laplace transform side. That still sometimes the Laplace transform will be helpful in those situations. So when it comes to inversion, there is an explicit formula. It's in terms of a complex contour integral, however. So you have to do something in the complex plane where you find some point sufficiently far out to the right so that all the nasty parts of the function are to the left, and then you integrate along some vertical contour like this. And it's a bit of a mess. We're not going to use it. If you take a complex analysis course, you might come across it. So the standard way that Laplace transforms are used for solving an initial value problem is as follows. So suppose we have a standard like harmonic oscillator type problem, so mass of m and a coefficient of friction by c and a spring constant k, and then we're forcing it with some forcing function f. And we start it with some initial position x naught and some initial velocity v naught. And so this is, one of these little mass spring dealies. Here's our mass m, and we've got coefficient of friction c and spring constant k. And we want to know how this thing bounces around, and we're pushing on it right here with some force F, pulling it backward and forward just to see how it responds. Okay, so taking Laplace transforms, what happens is that x double prime becomes s squared Laplace transform of x minus s times initial condition minus the other initial condition. And x prime becomes sx minus initial condition. And then we have the kx. And then we have the Laplace transform of f, which I'll write as capital F. And so then collecting the coefficients of x on the left, we have ms squared plus cs plus k times x on the left. And on the right, we have f plus ms x naught plus mv naught minus cx naught. And then we can solve for x, the thing we're trying to find. So we have some expression that looks like this. And then we invert the Laplace transform. So x here is going to be, let's see, by linearity, I can split this into two pieces. So I'll have L inverse of this guy plus L inverse of this guy. All right. And then this part is typically where you need to do all the work. So it turns out that the Laplace transform is additive but not multiplicative. So this part here is going to require some chewing for sure. This part here can probably be put into the form of something on the table fairly relatively easily. And then when you get that worked out, you end up with your particular solution plus your homogeneous solution. So this part here is most of the work. And so just sort of to notice there, you can see that the part where the forcing function makes a contribution is tied to the particular solution. All this stuff here is coming from the initial conditions, but if f is equal to 0, so you're looking at a homogeneous situation, then its Laplace transform will also be equal to 0. So this entire term is gone. And so that's how you can see that this guy corresponds to the homogeneous solution.